Okay, today we are going to talk about how to measure angle. So now if you use scientific calculators, you'll notice that there are two units of measurement when you're talking about angles. Do you remember what they are? Let's say you have an angle, then what's the common measurement?
You? Oh, degree.
Okay, and you see that on your scientific calculator, you have choice. One is say degree, another one. Do you remember?
No, I don't know.
You write like this. This is a radian. Good.
Yep.
Two measurement. Of course, degree we write like say 90 degrees. We use this degree symbol. And on the radian, do you remember what is 90 degree in 90 degree and equivalent in the radian measure unit? So 90 degree is equivalent to half pi. Okay, do you remember that?
You now.
Okay, 180 is pi. Good.
Yep.
Okay, so look at, we start with the degree measurement. Actually, degree measurement was pretty ancient. Even though in Euclidean geometry, we don't really talk about measurement, but it's still important now, especially we're dealing with circle. And we're going to looking at how to measure the angle. So that come down to is we have a circle, and first of all is the degree measurement. We actually break this circle into 360 equal part. If you look like that, this is the angle right in the center, then make another angle. So we cut this in exactly 360 equal part. So each one then is a degree, 1 degree. Okay, and this actually came from the ancient Babylonians. Now, ancient Babylonians are known for their star watching. Now, remember in the Jesus' birth, there are 3 people came from the east. And do you remember what they are called?
Wise men.
Wise men, and also another one is called the Magi. I hope I pronounced it right. So those 3 wise men came from the east, and actually those 3 wise men, and why they came to see Jesus?
Because there was a star overhead.
Right, right. Because they actually they are the star watchers, so they noticed that something unusual, and so they follow the star, and they believe that that is a sign that a very special person was born. And of course, we know that as Christians that Jesus, and those people actually from the east, and the east, that part actually is the ancient Babylonian, and in today's Iran and Iraq area. So they actually have a lot of record, and they actually use clay. And they use clay, and so they use the tool which just make a impression on the clay. So their writing is more like something like this. And then they bake the clay, and they use that as a record. I mean, preserve the record. So the actually archaeological discoveries or the archaeologists have found many of those clays, and one of clay actually was recorded, and how about this number, square root of 2. And they realized that that's more than 2,000 years ago. This number is irrational number, and their math, their number, their base is quite unusual. Like today, when we talk about like 100, 1,000, and even like 40 and 60 and 55, and we have a base. Remember, what is our base here? Now there are different kind of numbers. We know that in computer we use binary, which is base 2. So either at 0, 1. And now ordinary, I mean just everyday life, this is called the base 10. Okay.
Yep.
That means we have 10 digit, 0, 1, 2, all the way to 9. And this is this base 10 is very common in almost all cultures, but the Asian Babylonians is very peculiar. They actually use so-called base 60. That means their numerals actually is from 0, 1, 2, and all the way down to 59. Okay, that's the 10 numerals they use. So 60 numerals they use. And it very interesting. And so far, I don't think anyone has figured out why is that, why they use this system. But because they use this, and that's why today when we're talking about, we do have that base 60 system. Can you think about it? We talk about every day when you're trying to say schedule time for a meeting, or maybe you have a date, you have to say what time we go there. And so have you ever wondered, 1 hour is how many minutes?
60
60. Now 1 minute is
seconds.
60 seconds, and that's actually something we inherited from the ancient Babylonians. We use this base 60 system when we tell in time, when we have watch, and we just got it. So, you know, we take for granted, but that was history behind it. Why we have this strange way of counting time, because everything else is base 10, right? But we're using, when we count in time, we don't say it's an hour is, say, 100 minutes, 1 minute is 100 seconds. We don't do that. We actually use 60, and that's because that's what we inherited from them. And they actually established very sophisticated math, which allowed them to do very accurate calculation. But because they're a 60 system, and the way they when they watch the light sky back then, what is the center of the universe to them? The Earth. It's because that's where they're at. That's their reference. So that's the person who is looking for the stars, and they assume everything else is a sphere. All the stars are a sphere. So therefore, you have to record the movement of stars by looking at the degrees that the star has moved in a day. So that way they can keep a track. And so they have a circle, and they break the circle actually into 6 parts. So 1, 2, 1, 2, 3, 4. Oh, need 6. Okay, we got the center. Okay, we got one, two, three, four, five, six. Okay, so they break it into six parts, and each one is 60 degrees. So therefore, the whole circle is 360 degrees. So that's what we got from them. And so that's where now we use this kind of system as to how to measure a circle. But because when we're talking about circle, and we actually can pinpoint each one by looking at the degree. We can say, okay, this point, let's say this star is on certain day, little star here, it moved to here, and they can measure, okay, in this case, well, 60 degrees. And sometimes it's less than that, maybe just in a day, maybe just move like say 10 degrees. But they now have a way to record it, and so that they keep that as a record. And so later on, people can look at it and they could look like, okay, this star take how many years to go through the whole circle back to where it is. And so each one, they actually have very good record. So that is the measurement we have. So that's called degrees. And then in about 600 years ago, the Europeans and find that there another way to measure an angle, and it's also based on a circle, but their circle is called unit circle, which means the radius is one unit. And so in this case, they see, okay, instead of measuring the circle here, they're measuring the arc. Okay. And they notice that when the whole thing around a circle, so what's the length of that? That's our circumference. The whole, let's say, circumference is what? What's the length of a circle? I mean, the arc.
Degrees.
How long is that? The circumference. What's the formula for circumference?
Pi, 2 times pi times the radius.
Yes, 2 pi r. But in this case, our r is 1. So the circumference 2 pi. So if you look at the whole circle, if you just measure the arc, we got this 2 pi. But we also know that in terms of degree, the whole thing is 360. So therefore, we have this proportion is that 360 is corresponding to 2 pi. And that means 180 is just pi, and the 90 is just half pi. Good?
Yep.
And this measurement is very useful. And when you get into trigonometry and also get into calculus, we actually use radius instead of degrees when we do calculus. Okay, so now we have the two choice when we measure the angle, and this angle is called center angle because it's right. This vertex is on the center. So we can either use a degree measurement or we can use radius measurement. And also, we can also, when we measure the arc, we can also have two ways of measuring the arc. One is by, let's see, this circle is like this arc. And what is the corresponding center angle? So we can also use degree measurement for arc. Like for example, if we go 90 degrees, then the arc, let's say this is A and B, and we can say the measure, use M for the measurement of AB arc. We can also use 90 degrees. We can use degree to measure. Of course, we can also use the radius. Radius just have pi. Good.
Yep.
So that's about the measurement, and this very important, and we have to establish this, like how we measure an angle. Okay, so let's go over some basics when we're dealing with angle, just basic concepts. And even though in Euclidean geometry, those things are called proportions, we have to prove it. But for our purpose, we can just kind of go through it and just take it for granted. And we can focus on more interesting theorems. So we talked about last time proportion 1, which is about like given 3 points, you can draw a circle across all 3 points. And then proposition 2 means that if you have a circle and if you have the arc here, and if you have another angle here, so this is A and B and C and D, and this O. So that means if the angle AOB, which is this angle, congruent to angle COD, then the arc are equivalent. So the arc AB is congruent to arc CD. Okay.
Yep.
Okay. Then we're looking at proposition 3. And that is when you have a circle, and if this arc is equivalent, is equal to this arc, then the corresponding center angles, the central angles, called central angles, are congruent. So that means this is A and B, this is C and D, this is O as a center. So they said if AB is congruent to the arc CD, then the angle AOB is congruent to angle COD. Okay.
Yep. Yep.
So it's really the converse of the proposition 2. And then we're looking at proposition 4, is that if we have this is called a chord. It's called chord. And we have another chord. And here's the center. A, B, O, and C, D. So if AB, those are chord, is put line segment, is AB equal to CD, then the arc is also congruent. Okay.
Yep.
Yeah, so far, all those are pretty intuitive. And so we're looking at next proposition. Proposition 4 is when you have two angles have that. So this AB, OCD. So this one, if this angle are congruent to that angle, if AOB is congruent to COD, then the corresponding arc is congruent. Okay.
Yep.
This actually, oh, sorry, this is a 4, proposition 4. Oh, no, sorry, proposition 5, yeah. And then we're going looking at proposition 6. So proposition 6 is that you have a circle, you got a chord, and you got another chord, and of course there's a center angle. Okay. So it's AB and CD. So if this is proposition 6. So if AB is congruent to CD, I mean the arc AB and arc CD are congruent. That's why we put this on top. That means the arc. Then, not equal. So if the arc is bigger, same circle, if this arc is longer than this arc, then we know the chord, this chord is longer than that chord. Then AB is greater than CD. Okay?
Yep.
Okay, so this is going to be our last proposition for this class is 7. And basically is the converse of proposition 6. So that says if AB is equal to C, bigger than CD, so just kind of reverse of this proposition. If AB, so if this is bigger than this chord, then the corresponding arc, this arc, is going to be longer than this arc. Then AB is greater than CD. Good?
Yep.
Okay, so just kind of like a review, we'll kind of recap what we learned today. The proposition 1 is go through any 3 points, not on the same line, straight line, then we can draw a circle. And proposition 2 is that if this angle is equal to that angle, so their corresponding arc will also be congruent. 3 is if this arc is congruent to this arc, then the corresponding angles are congruent. And 4, talking about the relationship between the chord and the arc. So if AB is congruent to CD, then the corresponding arc AB is going to be congruent to CD. 5 is when the angle are congruent, then the corresponding arc are also congruent. And now we have this one. The 6 is the arc AB is bigger than CD, and then the corresponding chord AB is bigger than CD. And the last one, the proportion for this class, is the converse of previous proportion, is if AB is bigger than CD, then the corresponding arc AB is greater than CD. Okay, good.
Yep.
All right, so this is what we have for today, and I'll see you next time. Okay, next week.
All right. Thank you.
Yep. Bye.
Bye.